Okay guys, I know we have already gone over part of 3.2 part 3, but I just figured it was easier to record from the beginning and just kind of give a recap of what we did the other day in class. So we're going to finish 3.2, watch this video, and then you will have your A14 assigned as homework. So just as a review of what we were talking about the other day in class, Mr. Wilcox is extremely interested in predicting his two children's aptitude later in life. One way to predict later aptitude in children is by knowing in age, in months, when the child spoke their first words, so say daddy. A recent study of the development of young children reported the ages in months at which each of 21 children spoke their first word and their Giselle adaptive score. The result of an aptitude test was taken much later in life. Here are the data. So here's the data. It would all just go out in one band, but it's short, so it's cut off. So there's nothing different about this. It's just a continuation of data. But for example, this would be a kid that they talked to, 7 months old. That's when their first word was. And the Giselle adaptive score was a 113. This would be a kid that they looked at. The age of their first word was 10 months, and their Giselle score was a 100. Okay, so we could, in theory, put all of this data in lists in our calculator, and we could do our linear regression, and we could come up with a prediction equation. But the likelihood of all of us entering that data incorrectly and not having an error is probably slim to none. Like somebody's going to probably fat finger a 22 instead of a 20 or whatever it is. Let me see if I can get a clearer picture here. Maybe that's a little better. And so because of that, on the AP Stats test, they tend to lean more towards computer output. They're not so worried about can you put this in your calculator correctly. They're more worried about can you interpret your results. So this is from Minitab. So this right here is from a Minitab output, which is just a computer program. And it works just like your calculator. It took all of this data up here, put them into lists, and spit out its linear regression details. So things that we went over in class. You are always going to have the explanatory variable down here in context. So in this case, we're talking about the age of the child in months when they said their first word. Okay. Next to age, you will always find the slope. Okay. So next to the explanatory and context, that next number over, usually over what we call the coefficient, is going to be your slope. So the slope of our line is a negative 1.13. Then you also need to be able to find the y-intercept. You're also going to see constant. Okay, constant meaning not changing. Our y-intercept isn't going to change. So across from the constant, you'll find the y-intercept. So for this case, it's 109.87. Okay. Other things that we need to be able to get from our computer output. You are never going to use this thing over here, well, at least not in this course, this r squared adjusted. You don't have to worry about that. We don't use it, okay? But what you do want to look at are these two numbers right here. This is r squared. We could write it as r squared, okay? This over here is the standard deviation, but it's the standard deviation of your residuals, okay? Which we talked about, that's just an error of how accurate our prediction equation is. So our prediction equation is going to predict those Giselle scores with an error of about 11.02 points, okay? So we did start these notes in class. I'm trying to get it closer so you guys can see it better. The very first one says, what is the equation of the least squares regression line? So in context, I literally took the two numbers from our computer output and wrote them into the y equals mx plus b form. So we have our, in context, the score hat. Our predicted score should equal 109.87 minus the 1.13 times the age in months of the student, of the child that they were talking to, okay? Interpreting the slope, we talked about this also in class. They are usually always going to ask you to interpret a slope. That's just what they do. So for each increase in 1 month of age of first word, we're going to predict, remember you need to have predict in there, the Giselle score to drop, because it was a negative, by 1.13 points. Okay, so we had gone through that in class. We had also gotten through how to find R. So in our computer output, we did not have an R, but we did have R squared. So we literally took 41%. 41% is 0.41. And in order to get R from R squared, we just took the square root of that number, okay? The question is, where did the negative come from? Correlation always takes the sign of our slope. Our slope was negative. Up here it's negative. So you have to remember to add that when you write your correlation, okay? It should be whatever the slope is. If the slope is positive, your correlation is positive. If the slope is negative, the correlation is negative, okay? And if we were to interpret R, there is a moderate, because it's 0.64, that's like heading positively but not massively strong. So there's a moderate negative, I'm sorry, I said positively, heading negatively. There is a moderate negative linear relationship between age at first word and score, okay? The new stuff, things that we had not talked about before this lesson, was we hadn't talked about R squared yet. R squared is called the coefficient of determination. Coefficient of determination. They like to ask you what the value of the coefficient of determination is. They will use that phrase. So that is a vocab word that you need to get in your head and memorize it, okay? It tells us the percent of the variation in y that can be accounted for by the least squares regression line of y on x. So it actually tells us what the variation is and how much of it can be accounted for. So you could probably remember this in as a cookie cutter, because they like to do this as a C, like a follow-up C on an FRQ. So 41% of the variation in scores on the Giselle test can be accounted for by the least squares regression line of scores on age at first word. That should say word, not work. Okay? So that's just another cookie cutter that you're going to want to get in your brain and memorize, because it's always going to be the same. You're always going to talk about that variation of y. And I'm trying to get you guys a better image here. Okay, so if we make a scatter plot of the data, so we go ahead and we put all of that data into our list, and we just make a regular scatter plot, it's going to look like this graph right here. Okay, we have all of these kids that are like right here, and then we have child here, and we have a child here. Okay, if we make the residual plot, remember the residual plot is when we graph a scatter plot. We keep the x-axis as the same, but the y-axis becomes the residuals. Remember, the residual is just the observed minus the predicted. We get this thing. Notice child 19 over here on our scatter plot is child 19 right here on our residual plot. We were expecting a large residual, weren't we? Okay, child 18 over here is child 18 over here. Okay, so predict the Giselle score for a kid who spoke his first word at exactly 1 year. So I went and took in months, plugged it into my equation, and I should have gotten 96.35. The biggest mistake on that, guys, is that this contextual problem, the age is in months. Okay, so be careful on that when you go to do that one. Find the residual for this prediction. Okay, they like to do these as FRQs, A, B's, and C's. Okay, so they have you find the score because there's your prediction. Find the residual for this prediction, then interpret. Well, the residual is, if we go back and look at our data, exactly at 1 year would be 12 months, right? So if I find 12 months, the observed score was a 105. So I come back over here and I say observed minus predicted. So I have my observed 105 minus my predicted 96.35 gives me a residual of 8.65. Now I need to go ahead and interpret that. So the least squares regression line is going to underpredict the score by almost 9 points. Okay, almost 9 points. Okay, if you were to graph this, the dot would be over the line. So this is going to be a dot that's up here. That line is under it, so it's going to underpredict. Okay. Let's see. An outlier is an observation that lies outside the overall pattern of the other observations. There are two possible outliers, and we talked about those. They were child 18 and 19 if you look at our scatter plots. If you come back over here to look at the data, 18 and 19 are these guys right here. Okay. This was their age, 42 months. 42 months is when this kid gave their first word. Okay, that's a while out. So 42 months, they had a low Giselle score. This one was 17 months and had a really high Giselle score. Okay, so again, another outlier. So we went and found the residual for each outlier. So do that. So go find child 18 and do this process again. You're going to take their observed value minus the predicted value. Remember, the predicted value is the one that you actually have to plug into the equation for. If you do it correctly, 18 should give you a residual of a negative 5.54. No surprise, there it is on my graph. And 19, if you do it correctly, should give you a residual of 30.28, which, no surprise, there it is on that graph. Get my paper straight again. 10 says one residual is much larger. Why? So why do we get a 30 for child 19 and we get a negative 5 for child 18? Well, the reason is that child 19 is much farther from the least squares regression line. If you come up here, like, whoops, if you come up here, it's further away. This one is only an outlier because it's coming down this way, but this one's actually a distance is further, right? Child 18 actually pulled this line back this direction. If this wasn't here, this line would have come up a little bit, okay? So 18 actually made that stronger, okay? An influential observation is one that, if removed, would markedly change the least squares regression line. Let's see if either of the two outliers should be considered influential. So here is our equation that we're starting with. If we take child 19 out, the one that had the massive residual, this is our new equation, okay? It's actually fairly similar. If we take 18 out, the one that had the smaller residual, it actually changes quite a bit, right? So 18, even though it was a smaller residual, it's way more influential. And again, it's because if this wasn't here, this line is going to shift up, right? But if that one's there and this one isn't, we're still going to draw that line in approximately the same place, okay? So 18 is the more influential. And honestly, the reason why, guys, is 18 is an outlier in the x direction, okay? Notice it has a small residual, but in that x direction, it'll mess with that line a little bit more, okay? We would have done these in class. I would have had you guys done them in your group, and then we would have talked about them, but let's talk about them. Knowing which variable is explanatory and which is response is important for regression. Yes, you have to know what your x and your y are. True. Correlation and regression lines describe the strength of any linear scatter plot. Linear scatter plot would be true. It's false because I don't have that on your guys' notes, so I went with what you guys probably would have put there, but it should have said any linear. Okay. Correlation and regression are resistant to outliers. False, false, false. Correlation and regression are highly influenced by outliers. Okay. A high correlation means that one variable is causing changes in another variable. False. Okay. The key is that correlation does not tell us anything about causation. I can give you two things, which we're going to do this next week. We're going to do correlation stations. Two things that are totally unrelated that have high correlation. That does not equal causation. Okay, so you have to be very careful. Very, very careful. So that is all we're doing for that 3.2 lesson. So go ahead and start on those problems that are on page 191 at the bottom of your packet. I've also posted those in Classroom. That'll be due with this week's homework.